First question is a steel tube of length 1 meter stuck at one end. A person with his ear close to other end hears the sound of the blow twice, one traveling through the body of tube and other through the air. We need to find the time gap between the two hearings. So the first one, velocity of sound in air is 330 meter per second. In the box it is this much. Displacement 7 meters. So difference in the time period will be 1/3300 minus 1/5200. So it will give us 2.75 into 10 to the power minus 3 second, or 2.75 milliseconds. 10 to the power minus 3 is milliseconds. Oh, this is 1 meter. 1/330, 1/5200. Time is displacement over velocity. Now in the second part, at a prayer meeting, the disciples using Jai Ram, the sound amplified by a loudspeaker, comes back after reflection 80 meters away. Now what is the maximum time interval can be kept between Jai Ram, so that the listener can so that the echo does not disturb a listener. So this is the second one. Now distance that it will need to travel is 80 into 2, because once it will need to go 80 and then it will need to come 80, so 160 meter. Velocity is 320 meter per second, so time will be 5 displacement over velocity 160 over 320.5 seconds. So if this is the time gap, then we will if it is less than that, then echo will not be there. Now a man stands before a large wall at a distance of 50 meter, claps his hands at regular intervals. Initially interval is large, he gradually reduces the interval, so he starts clapping quickly. Now if he has to clap 10 times during every 3 seconds, find the velocity of sound in air. So first of all, he has to clap 10 times in 3 seconds. So frequency is 10 times over 3 seconds. So time period will be 3/10 seconds. Okay. Now time interval time taken to go to the wall. So it will be 3/2 into 10. So 3 into 10, 3/20 second. So velocity is displacement over time. Just to clarify again, 3/2 and 1/2. Why? Because this 3/10 seconds is for going and coming back. We only require for going. Okay. So 3/20 seconds will be required. Displacement 50, 3/20, 50 into 20 divided by 3, it will give us 333 meters per second. In question 4, a person can hear sound waves in frequency range 20 to 20,000 Hz. Find the minimum and maximum wavelengths of sound that is audible to the person. The speed of sound is given. It's quite simple. So this is the fourth one. So first for 20 Hz, wavelength is equal to velocity upon frequency, that is 320 over 320 and 20,000 hertz. Same 320 over, let's say 20 into 10 to the power 3 hertz. So it will give us 18 millimeter and it will give us 16 meters. No, 18 meters. So this will be the wavelengths. Find minimum and maximum wavelengths of sound in water that is in audible range for an average human. Now the speed of sound in water is different, so the wavelengths will be different. So this is fifth one. So same thing, same formula will be there. Wavelength will frequency will wavelength will be velocity upon frequency. So now in first situation where frequency is 20 hertz, we will have wavelength equal to 1450 over 20, and in second situation 20,000 hertz, wavelength equal to 1450 over 20 10 to the power 3. So this will give us 72.5 meter, this will give us 77.25 centimeters. In question 6, sound waves from loudspeakers spread nearly uniformly in all directions if wavelength of sound is much larger than the diameter of the loudspeaker. So we need to calculate the frequency for which the wavelength of sound in air is 10 times the diameter of the speaker. The diameter is 20 centimeter. When sound is essentially transmitted in forward direction, if wavelength is much shorter than the diameter of the speaker, you then calculate the frequency at which the wavelength of sound is 1/10 the diameter of the speaker discussed above. So what is in the question? So this is sixth one. So what do we have? According to question, wavelength is 20 centimeter into 10, that is 200 centimeter, that is 2 meters. Velocity is 340 meters per second. So frequency will be velocity over wavelength equal to 340 over 2 equal to 170 hertz. Now in the second situation, 340 over 2 into 10 to the power minus 2 equal to 17 kilohertz. Let me differentiate it. Here the wavelength is 2 centimeter, that is 2 into 10 to the power minus 2 meters. So this is one situation, this is another situation. Ultrasonic waves have frequency 4.5 megahertz to detect tumor. Now speed of sound in tissue is 1.5 km per second and in air it is 340 meter per second. So we need to find the wavelength of ultrasonic waves in air as well as in tissue. So similar formula, answer 7. So first for air, this is the velocity, frequency is this much. So wavelength in the air will be 340, that is velocity upon frequency, 340 upon 4.5 into 10 to the power 6, which will give us 7.36 into 10 to the power minus 5 meters. In the second situation, velocity in tissue is 1500 meters per second. Frequency is same, so wavelength in tissue 1500 divided by 4.5 into 10 to the power 6, which will give us 3.3 into 10 to the power minus 4 meters. In the 8th question, we have this equation of a travelling sound wave. Now we need to find the ratio of the displacement amplitude of particles to the wavelength of the wave and find the ratio of velocity amplitude of particle to the wave speed. So this is the 8th one. Now what are the things given? It is given that the amplitude is 6 into 10 to the power minus 5 meters. Next, now we know that 2 pi by lambda equal to 1.8. Lambda is 2 pi over 1.8. So amplitude over lambda 6 into 10 1.8 into 10 to 6 into 1 10 to the power minus 5 into 1.8 over 2 pi. So 1.7 into 10 to the power minus 5 meters. Oh sorry, this is a ratio, so no unit. Then in the second part, let's say velocity amplitude is Vy. So V is dy by dt. Velocity amplitude means the maximum velocity. Okay, so 3600 cos 600t minus 1.8 into 10 to the power minus 5 meter per second. So Vy, that is maximum velocity, will be when this cos term is 1. Let's try to write it differently. Cos 600t. So when this is 1, it will be maximum. So it is like this. Now the normal wavelength is 2 pi over 1.8, time period is 2 pi over 600. So the normal velocity is 600 over 1.8 equal to 1000 by 3 meter per second. So the ratio between velocity amplitude and normal velocity, that is maximum velocity and normal velocity, average velocity, is 3600 into 3 into 10 to the power minus 5 upon 1000. Okay, so this will get cancelled out. So Vy over V will be 36 into 3 into 10 to the power minus 6. In the 9th question, we have a sound wave of frequency 100 Hz traveling in air. Speed of sound in air is 350 meter per second. So by how much is the phase change at given point in 2.5 millisecond? What is the phase difference at given instant between 2 points separated by 10 centimeter? So this is the 9th one. So first of all, what is given? Frequency 100, velocity 350 meter per second. So wavelength is 350, that is velocity over frequency, 3.5 meters. So in 2.5 millisecond, distance traveled will be del x equal to 350 into 2.5 into 10 to the power minus 3. Milli is there, therefore this much, and velocity is 350. So velocity into time. So what is the formula for phase difference? Phase difference, that is del phi, is equal to 2 pi by lambda into path difference. So 2 pi over lambda is 350 over 100 and del x is 350 into 2.5 into 10 to the power minus 3. So after solving, del phi will come pi by 2. The path difference will be pi by 2. Now is the second part of this question. It is given that the separation between 2 points, let's say separation is del x, it is, or let's say del a, it is 10 centimeter, that is 10 to the power minus 1 meter. So phi will be 2 pi over lambda to del x, let's say del x. So 2 pi over 350 over 100 into 10 to the power minus 1, which will give us 2 pi over 35. In question number 10, we have 2 point sources of sound which are kept at a separation of 10 centimeter. Now they vibrate in phase to produce waves of wavelength 5 centimeter. So what will be the phase difference between two waves arriving at a point 20 centimeter from one source? Now A is on the line joining the source and B is on the perpendicular bisector. So this is the 10th one. So in first case del x is 10 centimeter, wavelength is 5 centimeter, so the phase difference will be 2 pi by lambda del x, which will be 2 pi over 5 into 10, which will be 4 pi. So the phase difference is 0. Whenever phase difference is pi, 2 pi, 3 pi, that is n pi, phase difference is 0. They are in same phase. And in the second part, again 0, because the particles are in same phase. As the particles are in same phase because they are moving in same path.